Fusion 360 Simulation Workspace offers a variety of simulation studies that enable you to validate and improve your designs for performance and manufacturability. You'll find studies that use linear materials, such as static stress, modal frequencies, shape optimization, and structural buckling, studies using nonlinear materials, such as nonlinear static stress and event simulation, studies to analyze the effects of heat transfer and radiation, such as thermal and thermal stress, and injection molding simulation, which looks at the manufacturability of high-volume parts. To purchase the simulation extension, click Extension and select Simulation. Select the free trial to experience the benefit of the extension before you commit. Once you're confident that the simulation extension is right for you, select Purchase Access using a credit card and follow the prompts.
In this video, we talk about modal frequencies simulation. Why would you use this tool, what the workflow and capabilities are, and what results it produces. All objects vibrate when acted on by an external stimulus. The vibrations occur at various natural frequencies and with varying shapes, each referred to as a vibration mode. Typically, you want to avoid exciting a structure at one of its natural frequencies, or the vibration will be amplified. This phenomenon is known as resonance, which can lead to fatigue failure. Conversely, in some applications you might want the object to resonate to maximize the produced vibration. An example is an ultrasonic cleaner or toothbrush. This model is a tuning fork like a technician uses to tune a piano. Here we see the fundamental vibration mode of 440 Hz, which is the standard A4 musical note. The length of the prongs has been fine-tuned in the Simplify workspace to achieve the target pitch. Now let's take a look at the process of setting up and solving the study. The first time you enter the simulation workspace, the new study dialog appears automatically. Choose the modal frequencies analysis type. Then, click this button to access the study settings. We'll choose to calculate 12 vibration modes. Analysis guidelines dictate what percentage of the structure's mass must participate in the computed vibration modes. These guidelines affect the number of modes you have to solve to achieve the target mass participation. We'll look at mass participation factors a little later in this video. You can apply global and structural loads to modal frequency studies. Tensile or compressive stresses increase or decrease the natural frequencies respectively. An example is the way the musical pitch increases as you apply more tension to a piano or guitar string. Activate the Compute Preloaded Modes option to account for the effects of applied loads. The tuning fork is not preloaded, so we'll leave the option unchecked. We'll define an absolute mesh size of 1.2 mm, resulting in 4 elements through the thickness of the prongs. This size should faithfully capture the strain gradients and produce accurate modal results. Next, specify the study material. AISI 304 stainless steel has already been specified in the model workspace, and we'll keep this material for the simulation. The model can be constrained or unconstrained. A tuning fork is lightly held in the fingers of the user. A rigid constraint would likely distort or impair the vibration modes, so we'll leave the model unconstrained. The displacement results are displayed as soon as the solution is finished, and the natural frequencies are listed for each mode in this drop-down selector. Since the model is fully unconstrained, we expect 6 rigid body vibration modes: X, Y, and Z translation and X, Y, and Z rotation. Animating the results provides good visualization of the modes. Note that the displacement results are normalized to 1 length unit maximum. The values aren't scaled to any particular excitation and are only meaningful for demonstrating the shape of the vibrating structure. You can't infer the stress level or the actual displacement magnitude, which depend on the excitation that drives the vibration. You can view the total displacement or the X, Y, and Z components of displacement. Mass participation factors are available from the Results drop-down menu. The factors are calculated separately for each of the 3 global directions and for each mode. The total cumulative factors are listed at the bottom of the table. Since this model is unconstrained, 100% participation is achieved by the translational rigid body modes alone. This behavior would not be the case for a partially or fully constrained structure. Thank you for watching.
In this video, we will discuss structural buckling. You may be wondering what buckling is and why simulate it during the design phase. The technical explanation is when an object is very long in comparison to its cross-sectional area and becomes unstable under a compressive load. You've probably seen this in plastic furniture or standing on something that wasn't intended to hold the weight of a person. The instability can end in a catastrophic failure, which personally I'd rather see on a computer. So let's avoid buckling early on. We are provided with a buckling load factor, which multiplied by the load will cause buckling. A value of less than 1 means that buckling will occur with the current load. Typically, we look for the lowest buckling load factor from the different modes. Let me show you how to set up and run a structural buckling study. We bring our geometry into the simulation workspace. Select structural buckling as the study type in the new study dialog. At this time, we can access the study settings and set the number of vibration modes. The displaced shape from buckling is based on vibration modes. The default of 3 is typically enough. We can also adjust our mesh settings. Now we can modify our materials if they weren't assigned in the modeling space. We can assign constraints to keep the model from moving infinitely. Fixing the bottom of the 4 legs is like if it were sitting in grass and the legs couldn't slide like they might on a slippery floor. Assign our loads. This can be determined by design criteria, or we could use a value of 1. The advantage of using 1 is that the load factor reported back to us will be the force required to cause buckling. We assign contacts that are appropriate for our model. In this case, the legs are coincident to the table, and we can use the automatic contact generator to create bonded contacts. Now, we can solve our analysis in the cloud. Once the analysis is finished, we have the same results mentioned previously for the different buckling modes. Since we used a load of 1, the buckling load factor is the force required to cause structural buckling. For this setup, about 195 pounds. I hope this helps. Happy simulating!
In this video, we discuss how a nonlinear static stress study can be used to evaluate the nonlinear response of an overloaded steel support beam. Here we see the displacement of the beam. The deformed shape has been exaggerated to make it easier to see. However, by default, nonlinear study results are rendered using the actual deformed shape. Let's review what's required to set up and run this study. The first step is to enter the simulation workspace and create a nonlinear static stress study. We can click this icon to see and adjust the study settings. As opposed to linear static stress studies, nonlinear studies are computed over several increments. This allows us to capture geometric and material nonlinearities. In this case, we'll use 60 increments. We'll also specify an absolute mesh size of 7 mm for the study. The CAD model material was defined as generic steel, which is a linear material. We can choose a nonlinear simulation material from the Fusion 360 Nonlinear Material Library, specifically high-strength low-alloy steel. Let's look at the nonlinear material properties. The simulation material is shown in the Document Materials list. The nonlinear data is located in the Advanced Properties section of the Physical tab. The material type is plastic, and the properties are defined by discrete stress-strain points in this data table. Nonlinear static stress studies are able to update the stiffness of the material throughout a simulation. Click this icon to see a 2D graph of the stress-strain curve. Slightly nonlinear behavior begins at about 230 megapascals, and nonlinearity becomes pronounced above 350 megapascals. Note that you can create your own custom materials to augment the ones listed in the predefined library. Choose an existing nonlinear material to use as a template. Then, click this icon to copy the material to your favorites library and open the properties for editing. Consult the Fusion 360 help for more information. The next step is to constrain the support beam. Apply a fixed constraint to this small face at the plus X end of the beam. Also, apply a constraint against movement in the Y and Z directions to the small face at the opposite end of the beam. These two constraints allow the beam to bend under the applied load and to float axially at the minus X end support as it bends. This setup represents an essentially simply supported beam configuration. Apply a 300 kN force acting normal to the top of the beam. Confine the force to the central portion only. The top face of the beam was split in the CAD model for this purpose. We can now solve the study. When the solution is finished and the results downloaded from the cloud, the safety factors at the last calculation step appear. Notice the low minimum safety factor, well below 1, and how much of the beam is red. A significant portion of the beam's volume has surpassed the yield stress, but it has not yet collapsed. Since we applied a 300 kN force and specified 60 steps, the load ramps up at a rate of 5 kN per step. The maximum von Mises stress at the end of the simulation is well over the initial yield stress of 234 megapascals. It is also significantly greater than the basic yield strength of 350 megapascals. The basic yield is the stress at which the material's stiffness is offset 0.2% from the Young's modulus. Finally, let's look at the displacements. The maximum displacement occurs near the midspan and at the top flange where the load is applied. The 2D graph of this result is particularly interesting. Notice how the displacement begins to increase exponentially beyond about the 35th step. Near the end of the simulation, the slope of the curve has become quite steep, and the beam is clearly on the verge of collapse. Thank you for watching. Hello. In this video, we talk about event simulation analyses, their purpose, workflow, capabilities, and what results they produce. Event simulation produces results common to other structural analyses, such as displacements and various stresses. However, It is not limited to static conditions or elastic materials. Nonlinear material behavior is supported. Large deformations and free body motion are supported, as well as contact interactions that can change throughout the simulated event. Velocity and acceleration results are available. You can simulate part breakage through the automatic elimination of elements from the mesh at strains above a specified value. Event simulation is a fully dynamic analysis tool, taking into account mass, velocity, acceleration, damping, and inertial effects. As such, it is useful for analyzing impacts, forming operations, and many other dynamic events. This model is a two-part snap-fit assembly, and we simulate the insertion of one part into the other. The locking fingers deform as they're pressed into the middle hole of the stationary part. Contact allows the parts to slide along and separate from each other freely, but prevents penetration. Let's look at the process of setting up and solving the analysis. Create a new study, choosing the Event Simulation Analysis type. Then, click this icon to access the study settings. Let's set a total event duration of 6 milliseconds and choose to save 12 sets of incremental results. We'll define an absolute mesh size of 3 millimeters, which will produce two elements through the main body thickness of the two parts. We're not concerned about stresses in the stationary body, and we can reduce the solution time by specifying that this body is rigid. Stresses and strains are not computed for rigid bodies. Substitute a stronger material for the ABS plastic previously defined in the model workspace. We'll use nylon 6/6 for both parts. Apply a constraint to the stationary part. Notice that it is recognized as a rigid body, and 3 rotational degrees of freedom are supported in addition to the translational ones. We'll keep the default action, all degrees of freedom constrained. Apply a prescribed translation of 10 millimeters in the -z direction to the front face of the moving part. This translation pushes the parts together. Leave the X and Y components active too, but keep the magnitude at 0. This technique prevents X and Y motion without having to apply a separate fixed constraint. Define a multiplier curve to specify how the displacement varies over time during the simulated event. This curve decelerates the part as it approaches the fully inserted position for a smooth action. In the first 2 milliseconds, the part moves 6 millimeters, 0.6 times the translation magnitude of 10 millimeters. Therefore, the velocity during this period is 3,000 millimeters per second. We'll need this velocity in the next step. Next, we apply an initial linear velocity to the moving part. This action prevents the shock of instantaneously accelerating the part at the beginning of the event. Essentially, we're saying that the part is already in motion at the beginning of the simulation. The speed, as we've just determined, is -3,000 millimeters per second in the z direction. Automatically generate the contact sets. We'll keep the default global separation contact setting, but disable self-contact. We don't expect any part to deform enough to contact itself, and not checking for self-contact will shorten the solution time. Ensure that the Select Through option is enabled under Selection Filters. In the next step, we need to select hidden faces of the model. To provide smooth contact surfaces and a more accurate contact solution, we need a local mesh control in the contact regions. Also, a finer mesh all over the locking fingers will provide better stress results. Let's set the size at 1 millimeter, or 1/3 of the global mesh size. Select all of the faces of the locking fingers and the middle hole in the stationary part. Then apply the mesh control. The study is ready to solve. When the solution finishes, the von Mises stress results appear. First, let's take a look at the mesh to see the local refinement we defined and hide the stationary part for a better view of the locking fingers. Now, take a look at the displacement results. We'll display a chart of this result versus time. Notice that the displacement curve matches the translation multiplier curve we defined during the study setup. We can create a slice plane for a better view of the part interaction and locking finger stresses. Choose a reference face and drag the slice plane to the desired location. You can also specify an exact offset. Here, an offset of 6.35 millimeters places the slice plane in the exact center of the part. From the browser, hide the slice plane so that it doesn't obscure the contour plot. We're interested in the bending stresses in the locking fingers to make sure they won't break due to excess stress during assembly. The normal ZZ stress tensor represents the bending stresses in the fingers. Drag the step slider to see how the stresses vary during the event. Finally, animate this result to watch the entire insertion event. There are 13 steps, one being the initial condition, plus 12 calculated steps. A setting of 26 steps here gives us 2 animation frames per step. Notice how the fingers oscillate in the last millisecond of the event after they snap into place. Analysis of many such assembly, disassembly, impact, and deformation events is possible using event simulation. Thank you for watching.
In this video, I'll discuss thermal analyses. You may be wondering, why should we run a thermal analysis? Thermal analyses provide us with temperature profiles and insight into energy transfer. This is most useful when we have parts that have a thermal failure criteria, like a computer chip, or when safety is a concern, like the radiator you see here. We want to validate that this radiator would be safe to touch while it is in operating conditions. Using probes and planes, we can obtain precise values anywhere in the model. Planes can slice into the model, allowing us to see inside the model as well as the external surfaces. Probes can be aligned to the model's external surfaces or placed internally as well. Let's walk through how to set up and run a thermal analysis. We bring our geometry into the simulation workspace. As we enter the simulation workspace, we are prompted to create a new simulation, so we'll select Thermal. At this time, we can access the study settings and modify our mesh settings if desired. Here, I'll assign the same mesh size that I used in the thermal tutorial. Adaptive meshing can also be enabled here. Adaptive meshing allows the mesh to automatically change due to the result gradients, and the solution is recalculated. This will increase the time it takes to solve the analysis. To save time while running an analysis, it is often beneficial to remove parts that are not necessary for the simulation. This is typically referred to as suppressing objects. To handle geometry changes for simulation, we do this in the Simplify workspace. In this analysis, we are interested in the temperature of the fins, so we can remove the fittings and the fluid. To remove them, I right-click on the bodies or components in the browser and select Remove. Materials can be modified if they were not assigned in the modeling workspace. We assign thermal loads to provide an energy balance. Heat in has to equal heat out. An applied temperature load will provide an infinite amount of energy to maintain the specified temperature, so it can be used as a heat sink or a heat source. In this case, the inside walls of the pipe will be at the same temperature as the water coming from the boiler/water heater. We apply a convection load on the fins where the air in the room would be removing heat from the fins. This load is calculating the amount of energy to be removed based on the reference temperature and the fin temperature. We want to be careful with the selection process not to select the area where the fins meet the pipes, as they will not be cooled by air in that area. Similarly, radiation loads calculate the energy transfer based on the reference temperature and the surface temperature of the fins. Radiation heat transfer can become the dominant form of heat transfer due to the temperatures in the radiation heat transfer equation being raised to the fourth power. This is especially true when natural convection is cooling your design. We define how the bodies contact each other. In this case, we'll use the automatic bonded contacts. Once the analysis is finished, we have the results ready to be inspected and interpreted. We can see that the temperature on the fins is pretty high and could be dangerous to a person that touches them. So we could decide to increase the size of our fins. At the end of the day, there is a cost associated to the extra material, but right now, finding out and understanding if we are under-designed or over-designed is incredibly valuable. Creating a new simulation model and rerunning the analysis with the same settings allows us to use the Compare workspace to look at results from both models at the same time. We can see that the larger fins reduces the temperature in the areas that people are most likely to touch. I hope this helps. Happy simulating!
In this video, we discuss how a thermal stress study can simulate the mechanical and thermal loads acting on a cast iron brake rotor and determine the resulting temperatures and stresses. This is an industrial brake rotor, much larger than the rotors on your car or truck. The simulation model is a 1/8 symmetry portion of the full rotor. Here we see the resultant stresses due to the applied mechanical and thermal loads. Let's take a step back and see what's required to set up and run this study. First, we need to create a new simulation study choosing the thermal stress analysis type. Let's go into the study settings and change the default stress-free temperature to 25°C. We'll also specify an absolute mesh size of 6 mm, which will give us 2 elements through the thinnest sections of the model. Of course, the production model includes the full rotor. We'll next go into the Simplify workspace to reduce the model to a 1/8 symmetry variant. Changes performed here have no effect on the production model. They are specific to the simulation process. Split the full model at each of the 3 global planes, which produces 8 separate bodies. Using symmetry gives us 2 advantages. First, the model size is reduced, which consumes less storage space and the solution time is decreased. And second, the application of constraints is very straightforward. We can fully constrain the model against motion in all 3 global directions without impeding the natural thermal expansion that we expect. Constraining thermal stress models can be tricky because over-constraint can result in severely exaggerated thermal stresses. Next, we determine which body is the one located at the nearest side in the first, or plus x plus y, quadrant. Then we keep this body and remove the other 7. We can now return to the simulation workspace. Notice that the model material has already been specified as gray cast iron, ASTM A48, grade 50. We'll keep this material for the thermal stress study. In simulation, when loads, constraints, and geometry are symmetrical, there is no motion in the direction normal to the plane of symmetry. So we constrain the following: the x translations on the faces lying along the YZ plane, the y translations for faces along the XZ plane, and the z translations for faces along the XY plane. Note that none of these constraints impede the radial or axial growth of the rotor as it heats up. Let's apply a pressure load of 13.8 megapascals at the hub bore to represent the load from the shrink fit between the shaft and rotor. This is the only mechanical load. The rotor is mounted to a water-cooled shaft, so we'll apply a fixed temperature of 38°C to this same face. We'll define a heat input of 36,500 watts per meter squared to the brake pad contact face. This value represents the average heat input to the rotor over time on a per unit area basis. The heat is generated as a result of friction between the pad and rotor when the braking force is applied. Lastly, we'll apply a convection load to all the exposed faces of the rotor, both interior and exterior, except for the brake pad contact face. This exclusion is conservative since we're ignoring the convective cooling along the portion of the face that's not covered by the brake pad. Do not apply thermal loads at the faces along the symmetry planes. Also, the program won't let you apply convection to the hub bore since we've already fixed the temperature of that face. The convection coefficient is 190 watts per meter Kelvin, and the ambient air temperature is 25 C. This convection value is higher than you would specify for stagnant air with only buoyancy driving the convection. The value takes into account the spinning of the rotor and therefore the higher speed of the air flowing over and through it. The model is ready to solve. When the solution finishes, the safety factor results are displayed. Notice the minimum safety factor is slightly more than 2.0 for the assumed conditions. Now we can toggle through the other available results, examining the von Mises stress, displacement, temperature, and heat flux. The area of greatest heat flux is where the slots are located. These openings allow cooling air into the rotor interior. Not surprisingly, this is also where the steepest temperature gradients and maximum stresses occur. Thank you for watching.
Electronics cooling in Fusion 360 enables you to simulate the temperature that components on an electronics board are likely to reach to determine whether the board is viable or if changes should be made. In this video, we set up an electronics cooling study to analyze the effect of heat-generating electronics components on the board and surrounding air volume. You can analyze an electronics design that was modeled in any CAD software. In this video, we analyze a design that was created in Fusion 360. This model is an assembly that includes 3 boards and an enclosure. To create an electronics cooling study, we need to switch to the simulation workspace and select Electronics Cooling. Notice that the electronics cooling study is associated with a simulation model. A useful feature in Fusion 360 is that you can create new simulation models, modify them, and analyze the changes without impacting the original model in the design workspace. Let's hide the data panel and set up the electronics cooling study ready for analysis. Often you can speed up a simulation analysis by manually removing details from the model components using the tools in the Simplify environment. In an electronics cooling analysis, this simplification is done automatically by the solver. The air volume around the board is also built automatically. The first task is to check the materials. Confirm that all the board components use appropriate materials and fix any with warnings. The only other study setup requirements are to set a thermal load on appropriate board components and to define fan attributes if the model includes fans. Since this model has no fans, we need only set the heat loads. For electronics boards modeled in Fusion 360, if the thermal loss for the materials were defined during the modeling process, the heat loads are imported automatically into the electronics cooling study. In this example, this wasn't done and we'll set the loads manually. In the browser, expand the Model Components folder to see all the components. We want to set heat loads on these 3 boards. Use the browser to show and hide components to make the job easier. On this main board, we'll set a heat load of 2 watts on this component. Click the internal heat icon to open the Thermal Loads dialog. Click on the component in the model to select it, and then type the heat load and press Enter to accept the value. Repeat the process to set 0.2 of a watt on these components, 0.1 of a watt on these components, and 0.08 of a watt on these components. You can see the internal heat loads you've assigned and edit them individually here in the browser, or you can see them all in one place in the Load Case Attributes dialog and edit them from here. At this point, the pre-check status confirms that there is enough information to run the analysis. While it's not required to solve the analysis, you can click Critical Temperatures to manually set critical temperatures on board components to highlight those that might overheat or fail. If your electronics design was modeled in Fusion 360 and the maximum temperature was set in the electronics design, this information is brought into the electronics cooling study automatically. Now we are ready to solve. When the analysis is complete, results are streamed from the cloud to provide you with immediate access to them and to eliminate the disk space requirements of large result files. Click Results to open the results viewer. The default result you see depends on your study setup. If you set critical temperatures on components, the risk factor result loads, showing you only those components with critical temperatures. This result helps you to focus on critical components that may fail due to overheating. If you haven't set critical temperatures, then the temperature view loads instead. This result view shows you the temperature of all the components in the model. You can switch between these results using these buttons. The section plane tool enables you to examine both the temperature of the solid components on the board and the temperature and velocity of the surrounding air volume more closely.
In this lesson, we will set up and run an injection molding simulation, look at the results and the guided results, identify options to try in order to improve the results. You'll learn how to clone your study to run with different setup conditions, set aesthetic faces, and compare results across different studies. Let's set up and solve an analysis to determine if the plastic bodies of this hedge trimmer design can be injection molded to produce good quality parts. The first time you bring a model into the simulation workspace, the new study dialog launches automatically. Choose the injection molding simulation study and confirm the target body if your model has more than one body. The study is set up automatically and is ready to run. The setup summary card lists the details of the default study setup and shows the material that has been selected, the processing conditions, and the number of injection locations. One injection location is placed automatically, so rotate your model if you don't see it immediately. Unless your design calls for a specific material, it's a good idea to use the default setup and then iterate with modification as dictated by your results. Click Solve to launch the analysis, and then click Results. As soon as intermediate results become available, the molding process is activated and you can check it for injection molding analysis information. The molding process tells you how the analysis is progressing, logs important facts about the analysis, and summarizes the results. You can view more results as they become available, and tooltips summarize what to expect from the results. The keyboard shortcut shown in the tooltips takes you to the online help, where you can find more information about what the results mean. Guided results are calculated at the end of the packing phase and are a good place to start to check the answers to the fundamental questions. Will your part fill? Will your part have visual defects? Will your part warp? You can access guided results both from the toolbar and from the molding process cards. The guided results show that under the setup conditions specified, some areas of the part will be difficult to fill, and this small area is unlikely to fill. The Visual Defects tab shows the presence and location of weld lines and sink marks, which could affect the appearance and structural integrity of the part. And the Warpage tab shows how much the part is likely to warp and where the warpage is likely to occur. You can move the sliders to match your part's actual tolerance to see if the warpage is a significant problem. Since this part must attach to other parts, it's also interesting to see how flat the matching surface is. What can you do if you want to improve the results? If you have the flexibility, changing the material is often a good option. The guided results provide more suggestions appropriate to the problem. In this analysis, to improve the likelihood that the part fills, one recommendation is to move the injection location. Clicking this button returns you to the Setup tab where you can make alterations to study setup. We have a specific material we want to use, so before considering other changes, we'll change the material to the one we actually intend to use. We'll clone the study so we can compare the two studies, then open the materials database and change the material. So you can check the properties of the material before accepting it. We'll also take this opportunity to select the aesthetic faces. That is, the faces that must look good and be free from blemishes. Once selected, aesthetic faces are highlighted for you in green. Now the study is ready to run again. Notice that pre-check is no longer green. The yellow warning means you can run the analysis, but the results may not be ideal. In this case, the injection location is on an aesthetic face, which will leave a mark. Let's move the injection location away from the center of the aesthetic face to somewhere else that, while still on the aesthetic face, is less obtrusive. And now we'll launch the new study. When the analysis is complete and all the results are available, go back to the results to view them. By default, the guided results open. The new study setup conditions look like they provide better results, but you can compare the two studies in detail in the results view to confirm. The fill confidence results tells you how likely the part is to fill. Enter compare mode, and select the other study for comparison. By default, the model viewpoint is synchronized, so you can zoom, pan, and rotate all models at the same time. Increase the number of windows, and you can compare the warpage results from the two different studies at the same time. Increase the magnification to see the deformation more clearly. As you continue to make changes, remember to clone your study if you want to compare, so you don't overwrite existing results. In this lesson, we set up and ran an injection molding simulation, looked at the results and the guided results, and identified options to try in order to improve the results. We cloned our study to run with different setup conditions, set aesthetic faces, and compared results across different studies.